So this is going to be the third video on Theta. So I'll go back to the previous video, follow the link to the OneDrive and download the file. So use the download option, open it up, enable editing, enable macros, and just rerun the data table as before. Explained this a few times previously, and it fills up. So I have various, I have the analytical data or analytical Theta for different stock prices. So this column here represents different S, and I've rerun the value of a call for different stock prices, but I reference T1, a lower maturity, and we have the value here, and we verified that it's the same as the value here. I did the same for the higher maturity, 1.25 years, so 15 months. But looks like I didn't. Hold on. Yes, I did N3, and the N3 here refers to this cell here. So just to verify that it's correct, that I haven't made a mistake, if I change this to be 1.25 years, or if I changed this value here, if I change it to 1, it should come up the same as before, and that's the simplest. So when they're both 1, we're getting the same results in both instances. So 1045, 1045, 1045, 1045. So I'm reasonably happy, satisfied that the order of the variables in the cell referencing is correct. Now let's change this to be a lower value, so 9 months, 3/4 of a year, and everything in the column updates, and I change this to be 1.25 years. And as before, what I want to do is generate a numerical. I want to generate a numerical value for the Theta, and the reference that I use is the lowercase t. Okay, so the change in the time period, what is the effect of the change in the time period on the value of the option? And we could think of it as a mathematical derivative. Again, if I go into Wikipedia, Greeks, options, Wikipedia, and just look for the reference to Theta, we can see that Theta measures the sensitivity of the value of the derivative to the passage of time. Not the maturity, but the passage of time. Okay, so again, it's important probably to emphasize the idea that Theta captures time decay. Okay, and we're getting a negative result. Okay, so if we go back into our worksheet, spreadsheet again, and perhaps I'll just copy and paste again and call it Theta 3. Just to maintain the order. Okay, now how would I work out this Theta 3? So if we're saying that the numerical Theta, numerical Theta was equal to this, then how do we estimate this? So we would say, okay, it's the option value, the higher option, divided by the lower option, minus the lower option value, and instead of going the higher time period minus the lower time period. We do it in reverse order. So it will be the lower period minus the higher. And that's just to make the value negative. We should get a negative value, and this should not be 0.075, it's 9 months. Okay, and we have a look here, and both are 0, relatively close to 0. Okay, let's pull that down and just make comparisons here. So it's comparing the analytical theta to the numerical, and there is quite a difference. Okay, but not dreadful. And again, if I compare this to here, there's some, if I compare here to here, there is some correspondence. And of course we could graph the outcomes just to, yeah, okay, so let's just graph. Okay, so if I insert a scatter graph, let's select data and just empty everything out and add, and the first variable will be the analytical theta, and the x series is the range of underlying asset value. So that's what appears here, or should appear. So let's take the values here. So that's the analytical theta, and it's negative, and it's negative because there's no positive range here. Okay, and put in an L. Okay, and then we're going to add another series, and we'll call this the numerical theta. And we have the x, same set of asset prices. So again, this axis represents the asset prices, and otherwise it's the theta value. And you can see, well, they're pretty close. In reality, they're very, very close. Okay, if we stretch it out a little bit, hardly any discrepancy at all. But, okay, however, if we just compare, if we just resize this a little bit, if we compare the analytical theta against the numerical theta, there are some small differences. Not enormous, but perceptible, perhaps. Okay, now let's just put this to one side. So I'll just park it over here and come back and say, how could we improve then on can we get the values to converge? And one possible way to get the values to converge is just to go, let's say, virtually close to 1 year for the short maturity, but not 1 year. And for the higher maturity, 0.1, and so virtually 1 year, but superior to 1 year. And now you can see very, very close convergence. So if I take this and compare here, okay, quite close, quite close, quite close, very close. So the negative 5.2144, negative 5, and again close. So that's what theta measures. It's a measure of time decay. The analytical formula we observe directly from the VBA code. Okay, so that's the VBA code for the analytical formula. It sprawls a little bit more. If I got rid of, even still, the analytical code disappears to bring back the Project Explorer. Okay, so it's quite a a big formula. If we go back into the spreadsheet, a simpler way of making that estimate and also offering some kind of rationale for the basis of the theta, it's just purely, if you think about this, the higher value for the call option, the higher value of the call option, so this blue minus the green, the lower value call option, divided by not the higher value but the shorter value for the maturity of the position minus the longer maturity. So we take the ratio of these, the differences, and divide by the difference in the maturities, and that also produces the same. The numerical theta as worked out here is virtually the same as the analytical data as given by the Black-Scholes option Greek formulae.